Um, Hello, everyone. Today we'll be talking about the presentation about the Lstm-based stack down to encoder. Authors have proposed a model that trains the model in unsupervised fashion. Pre-training part is in unsupervised fashion. However, the fine-tuning part, as we will see, will be in supervised fashion as well. So let's go ahead and talk about the motivation behind this paper. The first motivation is currently the most real-world data sets are multivariate, which means that we collect more than one feature over the time, which can be temperature, wind speed, and humidity, and so on. The second motivation is that we need the accurate modeling for the prediction with such data sets. And currently, we have already seen before the Lstm model, and with multivariate time series data, the Lstm prediction is not satisfactory because this approach initializes weights randomly, and we cannot learn correlated features properly, particularly when our time series data is long and big, and variables include high nonlinearity. So we have two problems in forecasting. The first one is univariate time series forecasting, where we're trying to predict some value in the future based on the previous values of the same signal. And we can denote it as we see with a formula where xi is being the time step, and we can have the multiple time steps for our data. And the second option, when we have multivariate time series data, where we're trying to predict the future value based on the same signal, and as well we are predicting based on the signals of other features. And in the formula below, you can see that J is being our feature and I is being the time step. So basically, for each time step, we can have more than one feature. In multivariate data, we have more than one feature. And in this paper, the forecast model will predict the output based on the past values and as well on the other feature. So it will be multivariate time series prediction or forecasting. To give an example, we can see on the left side univariate time series data, where we just have the signal and we have just temperature values. So for example, if we want to predict the temperature at, let's say at 9 p.m. over here, we'll be just using the signal of the past values. However, on the right side, we have the multivariate time series data where we have more than one feature or more than one variable. And if we want to predict the same temperature at 9 p.m., we'll be using the same signal, but as well, we'll be using the signal of other features to have more accurate prediction. One of the parts of this model of this paper is long short-term memory. However, before we'll talk about the recurrent neural network, which is the variation of Lstm is the variation of the recurrent neural network. And the problem of RNN is that it's difficult to learn a long-term dependency, especially when the time series signal is very long or we have a lot of data due to exploding and vanishing gradient. On the left, you can see how the process works. Basically, we will input the data of the current time step, and we will be passing the output of the RNN to the next time step, along with the input of the next time step. And on the right side, on the right figure, you can see the architecture of RNN, where we'll be passing the input, and we will have the output of the previous time step, and we'll do the operations including the input and the output as well to get some new response. As well, we can use the new response to predict some value using fully connected neural network or other method as well. Long short-term memory is designed to overcome the problem of RNN that we have the vanishing gradient. And to overcome this problem, we present a new cell that is capable of holding and learning long-term dependencies in our sequential data. So on the left, you can see the architecture of LSTM. This time, we will have two outputs of the previous cell. Over here, you can see this will be the output of the long-term dependencies. And on the bottom output, we will see the combined memory output. We can say it like that. And this time, LSTM cell will have a little bit different architecture because we'll be including 4 different gates, which is for get gate, input gate, gate cell, and output gate. For example, for get gate, we'll calculate how much information we want to forget from the previous response, and input gate will control how much information we want to include in the new response. And output gate will control how much information we actually want to pass to the next time step as well. Below the figure on the right, you can see equations, how we will get a new response and how we'll calculate the long-term memory and the short-term memory as well. But I have explained it in my previous presentation about the long short-term memory, so we will not go over it this time. Next component of the model will be autoencoder. Everybody's familiar with autoencoder from the previous presentations. The idea behind the autoencoder is that we will have the input layer and we'll have the output layer, and in between of input and output layer, we will have the one or more hidden layers. And our goal in the autoencoder is to minimize the reconstruction error. So we want to have our output as close or as equal as possible as our input. So the procedure of autoencoder is going to be that we will provide some inputs and we will map the inputs into the hidden layer. That's going to be our encoding part. And for the decoding part, we will try to reconstruct from our hidden layers to the output layer. And our goal, as I said, is to minimize the reconstruction error between the outputs and the inputs. So let's talk about the actually proposed model in this paper. It's called LSTM-based stacked autoencoder. So the idea behind that is original autoencoder architecture is being changed to LSTM base, and it is because LSTM is more suitable for the time series data, as we know. So we might capture some information better using the LSTM for our time series data. And our LSTM autoencoder will consist of 2 LSTM layers. One will act as encoder and the another will act as the decoder. So the encoder LSTM, if we see on the right picture, over here will be encoder LSTM layer. We will pass our inputs, and at the end of one pass, we will get some response over here from the last time step. We can call it H, hidden response, and we will use it as the learned representation, or in case of autoencoder, it's a hidden layer. We can name it like this. And for the decoder LSTM, we will use this hidden representation to feed. It will be our input this time for the LSTM. So over here, we will pass our hidden response along with here and here. But inside of the decoder LSTM, we'll be calculating the new response from each LSTM time step and passing it to the next time step as well. So we can call these guys HT. And using both these inputs, we can calculate the new predicted output X hat. We'll be using as well, authors have used as well mean squared error cost function to minimize the reconstruction error. And from here, using this architecture, we'll be able to stack this LSTM autoencoders to form the LSTM-based stack autoencoder, or LSTM SAE. Next, let's talk about the pre-training phase. It's called the greedy layer-wise pre-training. and we have may seen this architecture before. So as the first step, we'll be passing our inputs, and we'll be training our LSTM autoencoder based with our inputs to minimize the reconstruction errors from the decoder with the inputs that we have passed. After we have done this, we will save our encoder layer over here, and we will load this encoder layer to the second LSTM autoencoder block. But this time, however, we will not be training the encoder layer from the previous LSTM block. We will just block the weights, block or lock the weights, so it will just be one pass. And we will encode our inputs with our saved encoder and pass it to the next LSTM block. So we'll be training the encoder and decoder again and comparing our outputs of the decoder with the original inputs. After we have trained the second LSTM block, we will save the encoder layer as well. And this on the next pass, or on the next LSTM block, LSTM autoencoder block, we will be passing two encoders, one from the previous model and one from the first block over here. And we will log the weights as well. And it's just going to be one pass process, and we'll be training the decoder and encoder again and comparing it to the original values as well. At the end, we will load our three encoded layers, and we will use them to calculate the output. So we'll be appending the output layer at the end of the three stacked encoders. And authors as well proposed, in the previous research, they have proposed a deep long short-term memory model, which consists of multiple LSTM layers. And I will show you how it looks like. So on the right side, we can see over here, this model is deep LSTM. Basically, we stack LSTM blocks on top of each other, and at the last block, we can calculate some output. Okay, so the process of the fine-tuning will be as follows. We will load the LSTM encoder layers that we have found in the pre-training phase. And we will add this output layer, or we can say the fully connected layer, at the end of the three encoder layers. And we can initialize it with one neuron or with more than one neuron, depends on our problem. Authors have initialized it with the one neuron to be able to predict just one value. And fine-tuning phase will work in a supervised fashion, which means that we will provide the input and our output will be provided as well. So we'll be calculating the parameters and updating the weights in a supervised way. Input for this model is going to be multivariate time series data at each time step, and the output is going to be the predicted value at the next time step. So, for example, if we provide the data for today, let's say weather, temperature, wind speed, and humidity, we will try to predict the temperature for tomorrow. So authors have used two data sets in their paper. The first one is being the capital bag sharing data set, and that includes multiple features, and they're trying to predict the count of total rental bags for each hour. And the second data set is a PM2.5 concentration in the air of China data set. And it has 8 different features. And we're trying to predict the concentration of the air. As well, they have used 3 different performance measures. We have seen root mean squared error. We have seen mean absolute error, but however, in my case, I saw this SMAPA error for the first time. It's being the percentage error which calculates the symmetric mean absolute error using the observed and predicted values. And for the results, authors first have compared their proposed models, the new Lstm stacked autoencoder model, and as well their previous deep Lstm model. And they claim they have, before producing the results, they have found the optimal parameters, and using the optimal parameters, they have produced the results and decided which model performs better. So in the case with two models and 4 different parameter initializations, they have claimed that their Lstm stacked autoencoder performs the best. On the bottom, you can see the predicted and the original data using stacked autoencoder and as well deep Lstm with just using 1 layer. And on the right side, we are using 2 layers. The number of hidden layers, for example, for Lstm stacked autoencoder is being the Lstm blocks. We can say it like that. For the next case study, they have exactly the same parameters, and this time we're trying to get a result with the data for the concentration in China cities. And as well as the previous results, our results are better with stacked autoencoder using 2 Lstm blocks or 2 Lstm autoencoder blocks. And as well, the authors have compared their results with different models. They have used if we look at the table 6, they used their proposed model. They used their previous proposed model, and we have original long short-term memory, feed-forward neural networks, multiple linear regression, and so on. And among these models, their performance is the best, as we can see, using the SMAP error and mean absolute error. Thank you, and if you have any questions.